I hope you see my PowerPoint.
Yes, we are. Maybe you just put it on the presentation, yeah, but we are able to see it.
Okay. So today is our final session, and basically we will be concentrating on the analysis part of water budget components, and we'll use all the data we have just downloaded yesterday. So basically at the end of this exercise, you should be able to replicate the steps to estimate water budget components from the LDAS dataset at basin level and sub-basin level. And you should be able to compare dry and wet water budget components derived from GLDAS data. And so for homework assignment, you should be able to replicate the steps from this exercise to estimate water budget components from the Earth observation. And basically, you will only use precipitation data from IMAGE and terrestrial water storage data from Grace Foron mission. And I expect by close of Monday, you will submit your final output, which is the water budget estimate for precipitation and the terrestrial water storage in both seasons, wet season and dry season. And I will share my email as well in case of any issue. So the prerequisite of this exercise, you must have a GLDAS 2.1 monthly data, and that is about transpiration, precipitation, runoff, and the total water storage. We have downloaded it yesterday. You must have QGIS installed on your computer, and it is recommended the QGIS Stable Vision, specifically QGIS 3.4.6 as I earlier recommended for you all to install, because the latest one, which is QGIS version 3.16, is not stable yet, and that as some tools are missing or have been modified on their usage. So if you don't have this version, which is QGIS 3.4.6, you can still follow, but at some point you will require an already processed data to continue. But also you must have the import river basin shapefile saved on your computer and have a basic knowledge on QGIS and its processes. And basically all the processes we have just conducted in the first session. So this is the outline. We will start by importing data to QGIS platform, and then we will convert all units of water budget components to millimeter per month. Then we will estimate seasonal water budget components for wet and dry season, and then we will compare that water budget component for Limpopo River Basin and its some selected sub-basin, and then we estimate amount of water in each water budget component in the Limpopo River Basin. Okay, I hear some challenge on the chat. I found the challenge while using appears when I logged in. I got this internal server error. Okay, so the solution here is just change your browser. Try to use another browser and it will be okay. But there is a link to all the data sets. If you don't have the data set, you can go to Google Drive, to the link I shared yesterday. You'll be able to access all the data that we'll be using today. So this is a first step. So I request all to open QGIS so that we can start demonstration. I had already opened my ETZ. I hope you see QGIS platform. We can start our QGIS, guys. I will hold on for 1 minute or so for all of us to open QGIS so that we can continue together. Can we continue? Okay, so the first step is similar. You can just try to check your QGIS version. And as you can see, mine it is 3.4.6. It is Madeira. So basically, the first step is we are going to import data, and basically we will import the Limpopo River Basin shapefile, and then we will import our base map, specifically Google Satellite, using Quick Map Service plugin. So the procedure is similar. Just go to layer, and then add layer, and then add vector layer. Then here you can browse from where you have saved your files. Just navigate to where you save the Limpopo River Basin shapefile. Make sure you extract the file you have downloaded from the cloud, and just open and select a shapefile. It must have SHP extension. So select this file and open. And after that, you can just click add and close it. It will appear on a map canvas. So next, I'm going to add base map using Quick Map Service plugin. I hope you all remember how to install plugin. You can just go to plugin, manage and install plugin. Make sure your internet connection is on and well. And then on this search box, you can search Quick Map Service, and it is here. And you can just click install. But if you have already installed it, just click on this icon here. It is a Quick Map Service. It is written as search QMS. Just click it, and you can search Google, and all Google products will show up. And just search Google Satellite Hybrid. We are going to use Google Satellite Hybrid base map. So it is here. Just click add. Then you can cancel this window for Quick Map Service. Here it is. I hope we are clear.
Hello?
Yes.
I beg, we said we select Google what? Google Earth Hybrid?
Google Satellite Hybrid.
Okay.
Yes. Okay, so next we are going to change symbology of Limpopo sub-basin shapefile. So just right click on Limpopo River Basin layer and go to properties. And on this left column, just select symbology, and then use outline. You can use either outline red, outline green. You can choose whatever color you want. So I select outline red and change the color to blue. I prefer blue. You can choose any, and then click apply. You will see the output. So are we clear by now? Can we proceed to the next step? Okay.
Maybe I'm just lost on the fill color, simple fill.
On the?
When I'm fill color there.
Yes.
Because I see my shapefile being filled with blue color, yet I wanted just the outline.
Okay, there is a tab below. Do you find this tab?
Okay.
There's a lot of already styled colored. So you will find outline red. And from outline red, you can choose any color you want on this color option. Okay, so next step, we are going to import all our, I hope you see my presentation.
Yeah.
Okay. So after we have done importing our data, we are going to convert all water budget components units to millimeter per month. And as you can see, precipitation and the evapotranspiration data are in kilogram per meter square per second by default. So to convert this data to millimeter per month, basically kilogram per meter square, 1 kilogram per meter square is equivalent to 1 millimeter. So we are going to change only the second part to months. So we will take our data for precipitation and the evapotranspiration, then we multiply by 36,000, which is equivalent to a total second in 1 hour. Then we will multiply by 24 hours in a day. Then we will multiply by number of days in the respective months. And basically runoff by default is in kilogram per meter square, and it is accumulated over 3-hour interval. So basically runoff data have 80 different segments per day. As you can see, its SI unit is in kilogram per meter square per 3 hours. So to get for a whole day, you have to multiply by 8 to get 24, then multiply by number of the day in respective month. And the terrestrial water storage is already in millimeter per month, so we will be not converting terrestrial water storage data. And next, we will estimate seasonal water budget components, and basically we will estimate for which seasonal water budget components for dry season and wet season using these formulas. So for precipitation, we will just find a sum of our wet data. We will do the same for evapotranspiration and runoff, but for total water storage is somehow different. And basically, we will try to find change in terrestrial water storage for both seasons. Let's say for December 19, the data for information, the data for December 19, I mean, is reflected on January 2020, and that of January 2020 must be reflected on February 2020. And the data for February 2020 is reflected on March 2020. So simply, I can show you how to expand the formula of calculating terrestrial water storage. Okay, let me share this whiteboard. I hope you see this whiteboard. I want to demonstrate how to derive a formula for total water storage change.
Yes, we can see.
Okay, so as I said earlier, to get data for December 2019, it is expected on January 2020. So basically, to get data for December 2019, you have to take data for January 2020. 2020, I mean, minus December 2019. Then you have to plus. To get data for January 2020, you have to get data for February 2020 minus data for January 20. Then to get data for January 2020, you have to take data for February 2020 minus that of January 2020. To get data for February 2020, you do the same. You have to take data for March 2020 minus data for February 2020. And the last week, to get data for March 2020, you have to get the data from April 2020 minus data for March 2020. So basically, let me show how this formula can be simplified. As you can see, January, it is positive here, and you can find it negative here. So January 2020, it cancels January 2020. And basically February 2020 cancel out with February 2020. Then the same applies to both. some correction here to get data for January 2020. For December 2020, I mean, you have to take data for January 2020 minus data for December 2019. This is you will get data for December 2020. And to get data for January, you have to take that of February minus January. Then this is for February. So here you have to take data for March. You'll be required to get data for March. I don't know how to edit this, but basically to get data for February, you have to get data for March. So here it will be March 2020 minus February 2020, and then to get data for March 2020, it is the same. So basically, formula must remain as April 2020 minus December 2020. Okay, let me demonstrate it again to make this clear. I will start by finding data for December, January 20 minus December 2019 plus February 2020 minus January 2019. Then to get data for February, you have to take March 2020 minus February 2020. Then to get data for March, you have to take data for April 2020 minus data for March 2020. Yes. So basically, January 2020 cancel out with January 2020. Then February 2020 also cancel out with this one. And then March 2020 cancel out with this one. So basically what's remaining is negative December 2019 plus April 2020. So this is basically the formula we're going to use to convert terrestrial water storage. So for wet season, we will take data for April 2020 minus data for December 2020. And for dry season, we will take the data from October 2020 minus data for June 2020. I hope that is clear. Are we clear now? Okay,
Hello?
so we are going.
Hello? I thought when you have a difference, for example, February 2020 minus January 2020, you are able to get the data for January 2020. And then March 2020 to February 2020, that gives you February. And then April 2020, March 2020 gives you data for March.
Yes.
That was my interpretation. But when you say January is cancelling with February and then March, and then you have a negative December 2019.
Okay, I was trying to simplify this whole formula. So you can either use this one or you can either use this one. You will get the same output.
Okay, fine.
Yes. Okay, so we are going to start this conversion. Then we will estimate seasonal water. We will estimate, seasonal water budget components. So we will start with precipitation. So we have to add our precipitation data to QGIS platform by navigating to layer, then add layer, then add raster layer. We will now add in raster layer. It is not vector. Then click browse. Then navigate to where you saved your precipitation data from GLDAS, not image. This is the precipitation data, and be sure to input data for both wet season and dry season. Just open all your files and click add. You will see the output, and you can put this Limpopo River Basin shapefile upward. So we are going to convert this data from kilogram per meter square per second to millimeter per month. So basically, we will use one of the core function process of QGIS, which is called the raster calculator. It used to do any calculation you want to do with any satellite image or any data. So we will access the process under the processing toolbox. Just navigate on the menu bar and click process, then toolbox, and under this search button, just search raster calculator. Be sure to open raster calculator under raster analysis. So open this process. So basically, we are going to convert this precipitation data. All of these are precipitation data. So I will convert one by one. So basically, I will start with data for wet season. So I will start with this data for December 2020. These are all layers. So just double click on specific layer. Then we have to input our formula on this expression box. So as you see, I have already added precipitation data for December 2019. So I will multiply by 36,000, then by 24, then by respective number of months in January, which is 31. Then go under the reference layers used for automated extent. So basically, we will select our output extent here, but we will be replicating from the main layers that we used to convert, which is for this case is December 2019. So just select here 2019 and click OK. Leave all other options as default. Just navigate up to the output. We have to save an output file to our working directory. So just save to your working directory, the output. So just click this browse button and click save to file. So I'll save my file. So I will save it, let's say, as precipitation for December 2019. But let me put C to identify that this is already converted. So I save it here. Just click save. And after that, just click run. It is complete successfully. And you will see output on the layer panel. It is here, output. So you have to rename this output. Right click on this layer and click rename layer and just select, I rename as, you can rename whatever you want, but I will name as C, which is converted layer for precipitation for December 2019. Then click enter, and that we have finished the converting precipitation data for December 2019. So I'll go and convert data for January 2020. So I'll just delete this one for December 2020 and select the data for January 2020. Be sure to change under the reference layer from December 2019 to January 2020. Click OK, and be sure to save this file to your working directory. So I save it as precipitation for January 2020, and then run. You will see output here. Make sure you rename it. January 2020. I hope we're together.
Hello, I think for me, I'm a bit confused because I'm using QGIS 3.6, and then when I click on my raster calculator, it seems not to have the same functionality like yours.
Okay, do you see expression box, this expression box and layer panel?
Yes, I can do the expression, but then the other functionalities are not there.
Okay. Try to learn. Like
Okay,
I said earlier, yes, this QGIS versions vary a lot, but you can use it anyway. Try to learn, and we and try to give feedback if it fails. But
okay.
I don't think so. Yes.
Okay, I'll try it.
Can I get feedback from others? Can we continue?
Mine is giving errors, and it's saying something about the CRS, so the reference, spatial reference.
Okay, you have to select this reference layer. Here, you have to select this reference layer. Make sure you tick the data layer similar to what you have I selected on a expression box. So if you are converting data for December 2019, make sure you select also a reference layer for December 2019.
Yes, that looks better. Thank you.
Okay. So I'm going to calculate data to convert data for February 2020. I will just uncheck data for January 2020, and select this for December 2020, and be sure to do it the same under this reference layer. Just uncheck January and select February 2020. Click OK. Then save to your working directory. Then click Run. Then be sure to rename this file on the output layer panel. Then I'll just click rename to Conversion Precipitation February 2020. I will continue for March. Just uncheck February and select March. And save this file to your working directory. Then Run. Then I'll go and continue for data for dry season. So I will uncheck this data for March and select this one for June 2020. Then be sure to select also here data for June. And save this file to your working directory. Then Run. Be sure to rename as the output. Then I'll go for July. Then select July under the reference layer. Then save this file to your working directory. Then click Run. Be sure to come to this layer panel and save and rename this file name the same as you renamed it to your working directory. Then I will convert data for August. Then I will select August also under this reference layer and save this file to my working directory. And then I will run and rename also on the layer panel. So up to this point, I have completed converting all precipitation data for wet season and dry season. So next step is to remove all the original data which are in kilogram per meter square per second. So I will remove all precipitation data which are in kilogram per meter square per second. So just select all data that have such kind of SI unit. Yes, then right click and click remove layer. So here is the precipitation data that we had converted. So next, we will estimate season order budget as specifically precipitation for wet independently, and then we will finalize with dry season. So just return back to raster calculator. So basically, we will add for wet season, we'll add data flow December 2019, January 2020, February, and March 2020. So just input that formula and expression box. So start with December 2020 plus January 2020 plus February 2020 plus March 2020, and be sure to select the same layer. You just input and select on the expression box. So I will select data for December 2019, January 2020, February 2020, and March 2020. Then click OK. Then you must save this file to your working directory. So I save as precipitation, and it is for wet season. Then just click save, and you can run this process. It is complete. You will find an output here. Just name this output similar as you did. So precipitation for wet season, and just remove this layer. So we can remove this layer for wet season, or you can just go and convert and estimate water budget component for dry season by some all months that are in dry season. And basically, it is June 2020 plus February 2020 plus August 2020. Okay, we forget to convert data for September. We have to convert data for September also. So I'll just add the data for September. It is here. So I'll open raster calculator and convert data for September first to millimeter per month by multiplying it the same as we did to others. Okay. And number of months. It is 30. And then under this reference layer, be sure to select it. And you can save this file to your working directory. And then I click Run. Then I will remove this file. Then I'll go and calculate water budget for dry season by just find the sum for all months that are in dry season. Basically, it is from June 2020 plus July plus August plus September, which is output. I forget to rename it. So just under this reference layer, select all layers that you just input on expression box. So it is September, June, July, and August. Click OK and save this file to your working directory. And this must be precipitation for dry season. Then you can move other files, but okay, I see this is an error. Oh, yes, you can rename as PR for wet season. And basically, after calculating all precipitation data for season, that is wet and dry, you can remove all other layers. So basically, it is precipitation for dry, not for wet. So just scroll it up and you can remove all the remaining layers. So basically, we have done converting data for precipitation, but we have already saved them. So we can remove them too, so that we can start afresh converting data for evapotranspiration. So I hope we are clear up to now. Yes.
Before you go there, I was just challenged a bit with my version, but I figured it out and it is working well. So I was just a bit behind. I've finished converting all the units. Now,
yes.
I heard you talking about adding. So that's where I was lost because I was a bit behind. So for the dry, for example, dry season, which months are we adding?
Okay. So as I said for yesterday's session, for wet months we use December 2019, January, February, and March 2020. And for dry season, we will use data from June 2020 up to September 2020. So be sure to convert all those 4 months and then you add them up.
Thank you.
Yeah, so I'll go and convert data for precipitation. So I'll add first all data for evapotranspiration. Just be sure to select only TIFF file. There's 2 types of file in here. This is an XML document, so just select only TIFF file. It is only readable in QGIS. Here it is. So the procedure are similar. You have just to input to open first raster calculator, then you start converting. So basically, I will start with data for December 2019. Then I will multiply by 36,000. Then I will multiply by 24. Then you have to multiply by number of months. So basically for December, it is 31. So under the reference there, be sure to select also a data for December 2019. And then you can save your file to the working directory. So for this case, this is the evapotranspiration data. And it is for December. December 2019. So just click save and run. So I have already converted all this data for the sake of time, but you can do on your own. Maybe if there's any question up to this point before we continue to convert data for runoff, because it have different procedure on converting it. Then we will finalize by seeing how we can convert and estimate seasonal water budget for total terrestrial mean water storage. So are we good up to now?
Maybe I just, sorry to ask this, my expression of the adding the different months, it seems not working. Am I supposed to first open the brackets and then I select the months?
You can input operator using keyboard shortcut. It is not compulsory to use an operator displayed on raster calculator window. You can just use the keyboard shortcut, just find the plus icon and select it.
Okay.
Can I get feedback from others? Are we good to go? Can I continue?
Hello, sorry, can you explain why we are multiplying that expression by 3,600?
Okay.
Yeah, just to see clarity. I guess that's time, isn't it?
Okay, let me return to my presentation. So conversion. So here's the formula. So basically, precipitation data and the evapotranspiration data are in kilograms per meter squared per second, and we are required to convert into millimeter per month. So basically, 1 kilogram per meter second is equivalent to 1 millimeter. So we will leave this as it is. Then we will be dealing with only second. We convert second to month. So 36,000. There is 36,000 seconds in 1 hour. So I will just multiply precipitation data by 36,000 to convert second to hour. Then there are 24 hours in a day. So I will multiply them by 24. Then to get days to months, I will multiply by specific number of days in a month. So if it is December, you have to multiply by 31 days. Maybe if it's January, you have to understand January number of days in January at the specific year. If it's February, you have to understand number of days in February at the specific year. If it's March, you have to understand all that. I hope I'm clear now.
Yes, thank you.
Okay, can we continue? I want to demonstrate how we can convert runoff data. or light. So I will remove all the data from now, and I will just add runoff data. And I will use the same processes. I will use raster calculator to convert runoff, which are in kilogram per meter square per 3 hours. So we will want to convert 3 hours to months. So we will multiply runoff data by 8. So we will be getting kilogram per meter square per day. Then we will multiply by number of days in a specific month to get a kilogram per meter square per month, which is equivalent to millimeter per month. So basically, I will start with December 2019. December 2019 is here. So I just multiply it by 8. So for this case, it is now in kilogram per meter square per day. Then I will multiply by number of days in December, which is 31. Then be sure under the reference layer you selected December 2019. And then you can save this file to your working directory. So it is runoff. It's runoff for December, but it is already converted. Runoff for December 2019. So just click save and run. Make sure you name the output file on layer panel. Then you can proceed converting data for January. So I will remove data for December and select the data for January. But for this case, number of months is 30 for January. Then be sure to, under the reference there, you selected January and remove December 2019. And you can save this file to your working directory, January 2020. Then run. You will see an output here on the layer panel. So just name it as, let's say, a converted runoff for January 2020. So you can repeat the same procedure to February, to March, then to June, up to September to get the converted data. I hope you're clear. Maybe if you have faced any problem. I have already converted all the data. And for this, we can go now and see how we can convert terrestrial water storage.
Hello, this conversion also applies to February. Sorry, I was not. Is this conversion also applies to February? 8 times 8 times 30?
No, for February, I think number of months is 29, if I'm not mistaken.
Okay, so you should be knowing the number of days. What about the leap year and then the other year?
Yes, you must be changing. You must be seeing the number of days in a specific year. For this case, let's say for February 2019, it was 28 days. For 2020, it was 29. So number of days are changing. So you have to confirm it before applying this formula. Otherwise, your final value will be a little bit divergent.
Okay.
But it will be just a minor error. It will be a very small minor error. It will be a minor error. It's not a big issue. but just to maintain consistency, make sure you input the correct number of months.
Okay, thank you.
So if we are clear up to now, then I can move and demonstrate how to convert the list water storage data. If you are not finished converting data for Rano, you can download it from the drive I have shared so that we can align together. So I'll go and demonstrate how to convert either data. Basically, after converting runoff data, you have to, I forget here, we have to add all the converted data. Basically, to get data for wet season, we have to add data from December 2019 up to March 2020. And for dry season, you have to find the sum from the data from June 2020 up to September 2020. And basically for terrestrial water storage, I'll go and demonstrate it for now. All the data available on the cloud storage link I have shared yesterday, you can see, and you can try converting this data at your own time. Our time is learning quickly. So I'll just remove all this runoff data and add the terrestrial water storage data. Be sure to select only TIFF file. Then I will open and add to a map canvas. So basically, as I earlier demonstrated, terrestrial water storage are already in millimeter per month, so we will not be converting this data, but basically we will just estimating water budget components seasonally. So we will estimate for wet season and then for dry season. And as I earlier demonstrated, just to find terrestrial water storage, you can either use a long formula or a short one. You both will arrive at the same results. So we will use the same tool, which is raster calculator. And basically, we will start with estimating the terrestrial water storage for wet season by taking data for April 2020 minus data for December 2020. So I'll take data for April 2020 minus data for December 2019. And under the reference layers, just make sure you select the same file, which is April 2020 and December 2019. And you can save this file to your working directory. It is now at the terrestrial water storage for wet season. So you can just click run and you will find an output. It is here. You can just name terrestrial water storage for wet season. And you can do the same for dry season. Just you have to take data for September minus data for June. Then be sure to select also here. So it is now you have to take data for October 2020 minus June 2020, and be sure to select data for June 2020. For June 2020 and October 2020, it is here and here. And then you can save this file to your working directory. and click Run. You will see just the name for dry season. So are we clear up to now?
Yes.
Okay. Okay, so we have done converting all our data, and we have done estimating season water budget. So basically, I will remove all layer, and I'll be adding all the data layers that we have estimated. So basically, it will be a total of 8 data layer: precipitation for wet season, and precipitation for dry. So there is evapotranspiration for wet and dry season. There is runoff for wet and dry season, and the rest water storage for wet and dry season. So I'll go and select those data I have already prepared before. So you can just find this data also to the drive I shared with you. So it is here. The rest water storage for dry, for wet. You can find all. So I just open all these files. I'll cancel this window and just close up Limpopo River Basin file so that you can be able to identify these patterns. So for now, we'll go and see how we can change the symbology so that we can just assess a spatial difference in spatial resolution. We can just try to comment on seasonal water budget component based on spatial distribution of these values. So as you can see, this is the terrestrial water storage change for wet season. This is terrestrial water storage for dry season. This is a runoff for wet. This is for dry. This is the precipitation for wet. This is the precipitation for dry season. This is the evapotranspiration for wet, and this is the evapotranspiration for dry season. So I'll change symbology for terrestrial water storage for a wet season. So just right click on this layer and go to properties. And on this left column, just select symbology and go to render type, change to single band pseudo color. You must arrive at this window. You can then apply. You will see changes in color, but you can also increase number of classes by just changing on a mode. Just change to equal interval. Then you can increase as many classes you want. So I'll just put 10 classes. Then you can just click apply. So you can expand this drop down to have a view. So you can just try to visually comment on terrestrial water storage change in wet season. So basically, you can try also to do a quality assurance to determine some uncertainties on this terrestrial water storage data from GIS. As you can see, this data is not a bit high resolution. As you can see, this big pixels. So basically, terrestrial water storage is not appropriate to use if your basin is too small, like this one. This is very small. You will have a lot of errors and uncertainty to use terrestrial water storage. So terrestrial water storage is appropriate in our larger basins. So that is uncertainty I have to share with you. So basically, you can change the symbology of all layer you want. You can maybe change the you can maybe change the symbology for runoff for wet season. The procedure is the same. Just on a render type, change it to single band pseudo color. Then you can choose to increase number of classes also, but it is recommended to use one number of classes. If you use the 11 classes, be sure to use it also to other data layer. just to maintain consistency. And make sure you can use the same color lamp, or you can use different, depend on your ability to differentiate color. So I'll just use the same color lamp and click apply. So to see results for runoff for wet season, just uncheck this layer for terrestrial water storage for wet season, and then you can uncheck this for dry season to be able to view the results from runoff for wet season. Or you can just scroll this layer up, and you'll be able to access runoff data for wet season. You can expand this drop down for runoff for wet season, and you can start commenting and do a different quality assurance measure and so forth. So basically, that data set, I can say had middle resolution. You cannot use in a very small basin like this one, or basin, I can say. So basically, for this case, will be assessing water budget for an entire Limpopo River basin, and some selected sub-basin which are larger, so that we can omit any uncertainties that have heightened color and components are changing. Zonal statistics can help you extract value from these larger basins, or even estimating water budget component over this entire basin, the Limpopo River basin. So that is the one procedure that you can avoid these uncertainties. Basically, you can also do interpolation. You can just reduce this pixel size, but that can introduce another uncertainty too. So basically, whenever you use this data, make sure you verify with ground-based data at some point. And basically, when you are doing research with this data, make sure you just got some data for ground measurement, just for validation. So basically, next we'll go to see how we can extract value of water budget components using zonal statistics. It is a core functionality of QGIS. So just navigate to processing, and then.
Hello, before we continue there, I can see the shapefile for Limpopo at the extreme southeast. As if there is a portion that is not covered by the data set.
Of
That
course.
one. Yeah.
Of course, this data almost covers the land surface, as you can see here. It is not covering the ocean, and there is very small part which have missing data, which is here. And basically, as this model does not cover over the ocean, basically, when it's covered, the pixel will reach to the ocean. That's why it is pre-processed automatically. It removes automatically all the pixels that fall in the ocean. So that's why we have no data here.
Okay.
I hope I'm clear.
Yeah.
Yes, but it will not affect much, but it will have an effect, but not that much, because we are going to only find average water budget components over the entire basin of river of Limpopo. So basically, it will have an effect if you will only have to estimate seasonal water budget for this sub-basin. So next, we are going to use zonal statistics to extract value for water budget components. So just navigate to processing, then open toolbox. Then under toolbox, just search zonal statistics. And as I said earlier, this is where the problem starts. Zonal statistics have been modified across different QGIS versions. So basically, what the zonal statistics window you will be seeing here in my demonstration, it might be different to other QGIS versions. So there is a different way to use it across different QGIS versions. So it is here, zonal statistics and raster analysis. Just be sure to open zonal statistics. And I will be estimating seasonal water budget components over the entire Limpopo River Basin. So I will try to extract all value of water budget component for Limpopo River Basin. So under the last area, so I'll just start with evapotranspiration for dry season. So just select evapotranspiration for dry season. And then under the vector area containing zone, just make sure you select Limpopo River Basin, Limpopo River Sub-Basin, because we are interested with. And under the output column prefix, just input an output name of this layer you want. So for this case, I will write evapotranspiration for dry season. And under statistics to calculate, as I said earlier, I will be calculating average water budget components. So be sure to select average. So I will select a mean, which is average, but you can use any statistics you want, depend on the use case you want. And then click Run. It is completely successful. Then I'll go next to evapotranspiration for wet season. Just change on the last area and change on output column prefix. So I'll change it to evapotranspiration for wet season, and the statistics calculate is the same. I will calculate mean. Just click Run, and I will go to calculate precipitation for dry season. So I'll change output column prefix to precipitation for dry season, and click Run. Next is precipitation for wet season. I will change also to output prefix to precipitation for wet season, and I will click Run. Then next is runoff for dry season. So I will select runoff for dry season, then click Run. Then runoff for wet season. I will change output prefix into runoff for wet season and click Run. Then I will go to terrestrial water storage change for dry season. So I just change here terrestrial water storage change for dry season. Then I will click Run. Then I will finalize with terrestrial water storage for wet season. And I will change also output column prefix. Then click Run. So we have completed, and all the outputs you will find under this Limpopo River Basin attribute table. To access attribute table, just right click on this layer and open attribute table. As you can see, all the output is here, and all of this row represents sub-basin, Limpopo River Basin, Limpopo River sub-basin. So you can try to check them. So just select on a low number, and you will see a yellow strip highlighting the specific sub-basin you are selected. So these are basically
we can't see what we can't see your table.
You can't?
We didn't see your attribute table the way we are selecting.
Okay, let me start afresh. So to access attribute table, just right click and open attribute table. I think you are seeing, I hope you are seeing now.
No, your attribute table doesn't appear. We only see your map and the other things.
Okay, let me share. All right, you are seeing now?
Yeah.
Okay. So this is the attribute table I was talking about. So this number flow represents sub-basins. So you can just, let's say, click the first row to understand which sub-basin it is. So all effects will be highlighted on a map. So the first law represents this sub-basin. So basically, I'm gonna export attribute table to Excel so that to an extension which is readable in Excel so that we can do further analysis and some calculation, whatever we want, water balance, we can estimate water budget, whatever. So to export this data, just right click on Limpopo River Basin, which have embedded with all our data. Just click export and save feature as. Then under the file format, be sure to select comma separated values, CSV. This is an extension which is readable in Excel. Then you can save your file to any working directory. Let's say I'm saving here as the water budget. Then click save. Leave all other option by default. You can just uncheck this box. We don't want the output from this window to appear on our layer. We will be dealing with it on Excel or spreadsheet if you're using Mac. So just click OK. And as you see, it is successfully exported. So just navigate to where you saved your file. So I will navigate to where I saved my file. It is here. So I just open water budget. Wait a moment, I want to share Excel table. I hope you see my Excel table.
Yes.
Okay. Okay, this is the one we have just exported. So I will go and demonstrate how you can calculate averages, how you can do different water balances from the data. So basically, it's a normal Excel formulas that you can use you can input to estimate water budget component, can estimate average over the Limpopo River Basin. So basically, this is ideally presenting Limpopo sub-basins, and these are the areas for each Limpopo sub-basin. And this is the data for evapotranspiration for dry season, and as you see, it is me. And all of this data are in millimeter per month. This is the evapotranspiration for wet. This is the precipitation for dry season. This is the precipitation for wet season. This is the runoff for dry season, and this is the runoff for wet season. And these two are the water storage change for dry season and wet season. So you can find an average of each water budget component. Let's say I started with evapotranspiration for dry season. Just select and you can find average. It is here. Then you can find average for the rest of water budget components. And from here, you can try to compare this average water budget components over the entire river basin. So simply, if you see at the evapotranspiration for dry season, it has an average of 70. It is in millimeter per month. And basically, if you see evapotranspiration for wet, it is 254. it is in millimeter per month. So just you can compare how evapotranspiration change between dry and wet season. You can find the difference between evapotranspiration between dry season and the wet season by just finding difference. You can just find, we can even try to account for water budget using a specific equation for water budget. But what's important, we are going to find not absolute value, but we find total amount of water in each water budget component in Limpopo River Basin. So basically what you have to do is to convert all this data. It is in millimeter, so we have to convert it to meter. Then we will multiply by area, which is in meter square. So we will get meter cube. So that is the volume of water. So I will start with evapotranspiration data for dry season. And then I will select data for evapotranspiration for dry season for the first basin, which is here. Then I will multiply by 0.001 to convert it from millimeter to meter. Then I will multiply by specific area of each sub-basin is here to get data, to get this data in meter cubic. So here is the total amount of water for specifically for evapotranspiration for dry season for the first basin. So to get other basin, just I will scroll this down, and you can find also an average amount of water for evapotranspiration in dry season, and basically you will find as this amount. And we can go further to convert this information. It is in meter cubic now, so we convert it to billion cubic meter, which is the SI unit that is most used in hydrology. So I'll just convert this value to billions cubic meter. I will multiply by 10 power -9. And as you can see, it is now in billions cubic meter. So you will do the same for the rest of water budget components. I have already done so. Maybe I will just show you the output.
Excuse me, can you just repeat the formula for ET?
Okay, no problem. Let me delete all. Okay, so I want to calculate amount of water that is lost via evapotranspiration during dry season. So specifically, I will convert first this data. You have to remember that this data are in millimeter, so we have to convert this data from millimeter, and then we will multiply the converted data by area of a specific sub-basin. So basically, data for evapotranspiration for dry season, we will take that data for evapotranspiration for dry season, which is here. I will multiply by 0.001. To convert data from millimeter to meter, you have to multiply by 0.001. Then after that, I will multiply by area, which is in meter square. So basically, the output here will be in meter cube. And I will scroll down to get volume of other sub-basin, basically for evapotranspiration for dry season, and then last I will find average. Then after finding average, remember this amount is in meter cubic, so I want to convert this amount from meter cube to billion cubic meter. So I will multiply this value by 10 power -9. So I'll take this value times 10 power -9. Yeah, so this value are in billion cubic meters. So in the entire Limpopo River Basin, specifically in dry, evapotranspiration seems to have around 3.2 billion cubic meter of water lost during dry season. So you can estimate for wet season also. Maybe I can show you an Excel which I have already done it. So here it is. Here is what I was estimating. It is evapotranspiration for dry season. Here it is evapotranspiration for wet season. And as you can see, if we compare, this data are in billion cubic meter. So you can see evapotranspiration in dry season and in wet season. This is precipitation data in dry season, and this is the precipitation for wet season. As you can see, there is almost 18 billion cubic meter of precipitation in wet season over Limpopo River Basin, and in dry season it is almost 1.6 billion cubic meter. Here is the run of data, and here are the billions cubic meters of terrestrial water storage change in dry season, and this is for wet season. So basically, from this billions cubic meter or from this meter cubic, you can estimate different parameter for water balance equation. Let's say I want to estimate a precipitation minus evapotranspiration between wet season and dry season. So I will take maybe precipitation. Let's say we must have a total precipitation first to estimate, or you can use a seasonal based estimate, but it is recommended for water balance to use a yearly basis. And basically from the GIS data, you can either use seasonally, you can use monthly time scale, you can use the yearly time scale, or even a decade time scale, just to get an understanding of water budget accounting. So basically, if I want to account for water inflow and water outflow in the Limpopo River Basin, so first we must have a sum maybe. Okay, let's say we want to account for precipitation minus evapotranspiration for dry season only. So I must take a difference between precipitation for dry season minus evapotranspiration for dry season as well. So basically, if I'm trying to do it, precipitation for dry season it is here, then minus evapotranspiration maybe for dry season, you get this amount. This is the precipitation minus evapotranspiration for dry season. So as you can see, it is negative. So basically, in dry season over Limpopo River Basin, there are a lot of water that is lost via evapotranspiration than what is flowing in by precipitation. So that is one of the very easiest use case you can do, but you can do a lot more with water balance equations. So if there is any question, maybe I can answer it right now.
Yeah, for me, when I was exporting my attribute table to Excel, it so happened that I had a lot of columns compared to yours.
Okay.
Like for instance, I have next down, main sink.
Yeah.
Sub
Of course, I got you. That is normal. Even myself, I had that column, but I removed them. So that column must appear, of course, because it's just an embedded information for sub-basin. It is in the shapefile of Limpopo River Basin by default, but it is not generated by zonal statistics. This is the only column generated for zonal statistics, this one. But other column you're seeing is just to identify the Limpopo River Basin shapefile. It's an attribute for Limpopo River Basin shapefile. So you can just omit or delete them. They have no use case.
Okay, so that implies that you can as well do comparison per basin, because I think each basin is having ID.
Yes, you can.
Okay, thank you.
Okay, so I would welcome if there is any question.
Now, is it possible to generate a time series for these different parameters?
To generate
Time series, the time series.
time series, of course, but you have to download data maybe for a monthly, maybe.
Okay.
Yes. Then you can export each data for monthly. As you see, we had find a summation, maybe for evapotranspiration for dry season. If you remember well, we just find the sum between June data for June 2020 up to September 2020. So if you want to do time series, you have to skip that process. You have to export all data for each month. Then you can plot the data for time series as well.
Okay, fine.
Is there any other question?
Good afternoon, Frank.
Yes, good afternoon.
Yes, thank you so much for the presentation and the demonstrations. Unfortunately, I joined somewhere in the middle, but I was interested. What was the spatial resolution of the data set that we're using at the end for the modeling?
Okay, let me go back to QGIS. Okay, so as I demonstrated yesterday, GIS data have different spatial resolutions. It depends on which data you use, but basically for this data, 0.3 degree resolution, if I'm not mistaken. They have 0.3 degree resolution. That's why you see this big pixel. But you can just go to metadata of this layer to explore more about this layer. So as you can see here, it's pixel size. Hello?
Hello. So this is this 1 degree type.
Yes.
Okay, thanks. But yesterday I realized
almost 1 degree.
Yesterday we were downloading some data sets that were at 0.1 and 0.25.
Hello?
Hello? Hello?
0.1 and?
Yesterday we
Yes.
were downloading some data sets that were at 0.1 degrees, other 0.25.
Hello? Yes.
Hello? Yes, so my question is, no, which one is better? Why, what should I consider now before I utilize the 0.1 or 0.25 or the 1 degree? What's the benefit of the 1 degree over the 0.25 or the 0.1?
Can you repeat your question, please? I did not hear well.
Okay, I'm asking that since we have data sets that have got 0.1 and 0.25, what's the major benefit of using the 1 kilometer data when we already have the 0.1 and 0.25?
Okay. So basically, it depends on your use case, specifically on your study area. If your study area is too large, you can use even data for 1 degree at times 1 degree spatial resolution. It will have a much smaller uncertainty. But if you have a small study area, you have to find the data with a large resolution up to 0.1 degree. I hope I'm clear now, but for our case, we have just downloaded data for 1 degree times 1 degree resolution. So the data we are just using, it is in 1 degree spatial resolution, but data for remote sensing have much higher resolution. So it depends on your use case. If you had a small basin, you have to find the data with higher resolution. Otherwise, it will be not accurate. It will have a lot of uncertainty attached to it. I think I had answered questions.
Thank you so much for the response. Thank you.
Frank, I've got a question about how you estimate the volume of water that's available in the rivers. Would that be
Okay.
the runoff component? Or is it also the change in terrestrial storage? So some of this water is sinking into the ground and then returning as base flow into your rivers.
Okay. So basically, you're asking about terrestrial water storage, right?
Yeah, what is that terrestrial water storage?
Okay. This is a terrestrial water storage for dry season. And as you can see, it is negative. And maybe because in dry season, there is high, maybe sunlight, wind movement. So a lot of water is lost from underground, from surface storage. That's why we get negative. But basically for wet season, it is almost positive because we have a lot of maybe precipitation. And point to note that this data, Grace followed mission data, currently did not embed in anthropogenic water withdrawal. So that option is selected out. So it is just a natural process that is affecting terrestrial water storage amount.
So that's basically groundwater.
Yes.
Okay, and if I need to calculate the volume of water that might come down the rivers in the Limpopo Basin, which value would I choose?
There is another data for base flow. We did not consider in this case because all base flow amounts from data specifically over the Limpopo River Basin is almost negligible. It is 0. That's why we have this neglected it. But if you want to calculate amount of PS underground water, you can use that data for base flow.
So one would use the runoff almost entirely.
Okay, this is it is calculated, of course. It is the difference between precipitation and evapotranspiration.
Okay.
That is how GL calculates runoff data. Yes.
Okay.
So even if you are dealing with satellite imagery, a runoff is not calculated directly from the satellite. It is estimated by taking precipitation data minus evapotranspiration data.
Okay.
Yes.
That's clear.
All right.
Excuse me, Frank, another question, not technical though. Are we gonna have an evaluation exercise of some sort, or?
Yes, of course. Our assignment.
On the practical side.
Yes, we will do an assignment on the practical side. Basically, we will be using remote sensing data. It requires similar steps as we did in GLDAS, but
we'll be using those other data sets.
Yes, for remote sensing, and there will be specifically more for precipitation and terrestrial water storage. So there's nothing different, only spatial resolution. Remote sensing data have very high spatial resolution. Yes.
Okay. Yeah. Thank you so much.
Okay. So maybe I can share my email if we get any error. You can reach out.
Yeah, would it be possible for this session to be shared with us before we do our training, our like exercise, because somehow I missed some steps.
Okay. I will share there's a manual, of course. I will share the manual.
Okay, okay.
You can follow the same step as written on a manual to reach.
Okay, then the other
Minus
question. The other question is on total water storage. I have a feeling I was reading about it, and that this is a summation of soil moisture. There is snow and whatever. So would we, like I had as if maybe right, not right, calling this value to be the groundwater?
Basically, not really groundwater, but terrestrial water storage data including soil moisture, including data
The snow.
from, as you say, snow, including data from rivers, lakes, all our terrestrial water storage data.
Okay, fine.
Yeah. So I hope there is not any other question, but I don't see alternate. Who is the host?
One more thing, Frank, something just popped up. I remember yesterday when we were downloading the groundwater storage data set, instead of downloading the 4 months of interest, I think we downloaded 5 for dry and 5 for winter. And is it correct to, if I heard you correctly, that for each month we take 2 months? For example, if we want to calculate the storage for the month of July, we subtract the difference between July and August to get July. Is that correct?
Yes.
Okay.
Yeah.
So these procedures, like having, let me give an example of Eastern African country where we have 2 rain seasons and I think, 2 dry seasons. So the kind of procedure will change a bit because I know they have MAM and SON.
They have what?
March, April, May as the first rain season, and then September, October, November as their second rain season.
Okay, so as you said earlier, it depends on your use case. If you want to estimate seasonal water budget components amount maybe of East African region, you have to understand what is the wet season months in East Africa region so that you can download the specific data for month season. So basically, if you want also to download data over the entire year, that is quite simple. You can download all 12 months and estimate water budget component of a specific year. So it depends if you are working with either Northern Africa, Eastern Africa, they all have different climates, different seasons. So you must understand which season and which months are included under the specific climatic region. And basically, it is important to understand as a specific number of days in a month you are dealing with.
Okay, thank you.
Yeah. And I see you, Peter, you are host now.
No, I'm not the host. I don't know what happened. I'm just using 2 computers to follow up. One is to listen, another one is to do the practical session.
Okay, can you transfer the privilege to me?
Let's see. I beg your pardon?
Can you transfer a host privilege that you are to me? Just allow me maybe as a co-host so that I can
So that means I go to settings?
Oh, I don't think so. There is an option to transfer. I think, host privilege, because if you end this meeting, you will, I think you will have a recorded video saved on your computer.
Just trying to find what you. Okay.
Frank, we can still see your screen, so you still have some privileges.
Okay. Okay, just to wrap things up, I will share the task over the platform, alternate platform. You will find the task to do, but basically you have to estimate water budget components, but you will be using precipitation data and the less water storage, but from remote sensing datasets. So for precipitation, it must be image data, and the less water storage must be from a glass colon solution. So just you can follow the similar procedure we have just done here. And I will just need an Excel sheet. I highlighting amount of water budget components for precipitation for both seasons, and the less water storage for both seasons. So that is the only task I would like to share with you. And I have already shared my email. If you get any difficulty, reach out to me. And lastly, I think Peter, you can end up the session and make sure that recorded video you sent it to me, so that we can process it and share for you to follow.
Okay, then are you going to share with us the assignment in terms of writing, or the way you have just talked about it? That's all.
Of course, I will share it on the platform.
Okay.
I think there's an option to access all tasks over there.
Okay.
I will write the documentation and upload on the platform.
Okay, thank you.
Yes.
Can I stop?
Not, yeah, you can stop that.
Okay, thanks.
Yes, make sure you share with me this recorded version of this video.
Okay, fine.
Okay, thank you. Goodbye.